Morning, dear students. Last session we have talked about this basic concept in pre-stressing. Let's proceed to the contents in this session. So I'll just run through these slides, whatever we have discussed in the last session. And today's session we'll talk about early attempts of pre-stressing. So this picture, what you see here, will depict what exactly is pre-stressing is done. So pre-stressing of structures was introduced actually in late 19th century. From there onwards, it has picked up. Latter part of 19th century is very crucial in the development of pre-stressed concrete. Then further it's, 21st century, 20th century, it is going to be like vast applications, you can say. So the sketch that you see here, this one, we take a mold. So this is a mold where it is empty and a rod is inserted and it is fixed at one end. The one end of the rod is tied, then the other end of the rod is being pulled. Okay, so place and stretch mild steel rods. This is the early attempt prior to concreting. And once the stretching is done, then we pour the concrete. Once the concrete gets set, the rod is released, then cut the rod after concreting. So this is the early attempt of the pre-stressed concrete preparation. And once the pre-stressed concrete member is ready, then its application as beam we will see now. So mild steel rods are used for stretching because the in 19th century mild steel rods are being developed. Concrete is poured around them. After hardening of concrete, the tension in the rods is released. Okay, the rods will try to regain their original length. As the rod is inserted in a hardened concrete, it prevents the regain of the length by the surrounding concrete. Hence, the concrete will be in the state of pre-compression. So, the pre-compression is introduced in the concrete. So, it is capable of counteracting tensile stress, which will arise from the following. The diagram will explain you that the beam which is pre-stressed is now used as just as an example. If it is a simply supported beam, let us say, so this is going to bend like this under the load. So the bottom face which is under tension, the upper half of the concrete will be in compression, the lower half of the concrete will be under tension, and this tensile stress, which will be counteracted by the compressive stress which is already there in the concrete. Okay, so that the beam will be finally in compression, maybe in compression, or you can reduce the level of tensile stress. This is the basic uh, need of the prestressed concrete, where to eliminate the tensile stress or to reduce the level of tensile stress. Right. This was the very early attempt of the prestressed concrete, where to take a mold and insert a rod, tension it, then pour the concrete. Uh, Once the concrete is set, release the rod, where the reinforcing bar will try to regain its shape. So in that process, it will try to apply compressive stress in concrete. So that compression will uh, counteract the tensile stresses to come when it is used as a beam. Okay. So that we can enhance the strength of the beam, so that the more load you apply, the more tensile stress will develop. Uh, the tensile stress, the more the tensile stress that is developed, and that is being counteracted by the concrete. So vice versa, the compression required may be calculated based on the application that you want, for which the beam is used. Okay, so this is how the early attempt is made, but the early attempts of pre-stressing were not successful because of the following reason. What could be the reason for the failure of the early attempts of pre-stressing? It was observed that the effect of pre-stress reduced with time. So there is time factor involved, which means, say for example, we have induced 100 megapascal compressive stress in the concrete. As time progresses, the 100 will come down to maybe 50 megapascal or maybe to 0. So as time progresses, compressive stress that is induced or pre-stress that is induced is vanishing or diminishing. So that is one reason for the pre-stressing, early attempts of pre-stressing failure. And also the load resisting capabilities of the members were limited. Under sustained loads, the members were found to fail. This is due to the concrete shrinking with time, and the sustained loads, which are time bound loads. Strain in concrete increases with increase in time. That is also known as creep phenomena, that you have studied in your reinforced concrete structures. Reduction in length due to creep and shrinkage is also applicable to embedded steel, where resulting in significant loss in tensile strain. So both creep and shrinkage is also there for steel, not only for concrete. So the reduction in pre-stress is also possible both because of concrete as well as steel. The early applications of the prestressed concrete is on mild steel only. Uh, so the strain due to pre-stressing what we can develop was very less. So the residual strain, in turn the residual pre-stress was only about 10% of the initial value. This is very astonishing number that you can see, that which means if you induce a 100 megapascal stress, finally what will remain is only just 10% of it. Okay, so which means if you induce 1000, then it could be 10% of that 1000. So likewise, the final pre-stress, that after accounting to all these parameters like creep, shrinkage and all, you are having only the effective value just 10% of the stress that is being induced in initially. So this is the reason for the early pre-stressing attempts failure. Okay, so that is also explained in terms of numbers. Okay, so take a member and try put it in terms of some numbers. Okay, so if you take a mild steel rod, the allowable stress for mild steel is only 140 megapascal, divided by Young's modulus of steel will give you the strain, which is 0.0007. The total loss in strain due to elastic shortening, creep and shrinkage of steel is also almost close to 0.0007. Means what? Whatever you are stretching the steel bar, the value of strain that you are creating is lost because of these things: elastic shortening, creep, shrinkage. So whatever is induced is completely lost. So residual is almost zero. Means the stress that you created initially is getting lost. Finally, you are getting the remaining value of stress is almost zero. So there is no point in calling a member a pre-stressed concrete member when it is having zero pre-stress. So this is the problem with the earlier attempts of the pre-stressing. Okay, so what could be the solution to increase the remaining value of stress? That means the value of pre-stress. To increase the pre-stress, what you need to do, the loss value is almost fixed. This is around 0.007. So if you are able to increase this value, which means some 0.001 or something, 0.002 or something like that. So this minus this will give you the residual strain that is proportional to the residual stress. So your attempts shall be in the direction of increasing this value. When you try increase this value, then you will have increased pre-stress value induced in the concrete. So this to do that one, what you need high strength steel. Not mild steel is not sufficient, because the strain of mild steel, the maximum that you can induce is only this much, 0.007, because allowable stress is fixed for this, because you have 250 is the yield stress. Mild steel Fe 250 grade. 250 is the yield stress you have, and allowable is only 140. So unless this is a fixed number, this is a fixed number. 2 into 10 power 5 is fixed. So unless you increase this value, you can't increase this value, residual strain. So to increase this one, what you need? You need higher grades of steel. So that is what is told. Adopt high strength steel, which with much higher initial strain. This leads to scope of high pre-stress value or high pre-stress force, and that is not sufficient. If you try adopt high strength steel, the concrete that you are using shall be capable of taking that stress. So just nominal concretes of M10, M15, M20 are not sufficient. So you need to increase the concrete strength also. Okay, so adopt high strength concrete to withstand that high pre-stressing force. So these two are very crucial requirements that are have come out actually from a failure where uh, it was started with the mild steel rods, the pre-stressing concept in concrete. In fact, we started with the mild steel, and they found that after some time, the residual value of the stress, that means the value of pre-stress, is almost becoming zero. And what is expected, it is not the value that they are getting. Hence, the need for high strength steel and high strength concrete is mandated. Okay, so this is what is required with the early attempts of pre-stress that we could find. Okay, right. Let's go to the history, very brief history of pre-stressed concrete, how it started, how it got progressed. Okay, so in 1824, the name cement is being manufactured by Aspidin, England scientist. So he obtained patent for manufacturing of Portland cement in 1824. Then 1857, Monnier, a French engineer, introduced steel wires in concrete to make flower pots, pipes, arches, and slabs. So from there onwards, the pre-stressed concrete is being very significant. So the first and foremost, Monnier is the one who thought of introducing steel wires into the flower pots to make flower pots, to introduce steel wires in concrete. Okay, so this is where the thought started. Next, 1886, Jackson from USA introduced concept of tightening steel tie rods in artificial stone and concrete arches. This diagram depicts the same. So artificial stone and concrete arches are being tightened with a steel tie rod. Okay, so there is also a type of pre-stressing. Then in 1888, Doring from Germany manufactured concrete slabs, small beams with tension steel. 1908, Steiner from USA recognized losses due to shrinkage and creep, suggested retightening the rods to recover lost pre-stress. This is also one good, interesting findings from the history of pre-stress. So you are losing the pre-stress value, you know it. So the thought of the initial thought is to retighten the rods again. Again, pull the rods to have the stress, and this cannot be called as pre-stressing. It is re introducing the pre-stress. So whatever the loss of pre-stress we have, that is regained again by retightening the rods. And again in 1923, Emperger from Austria developed a method of winding pre-tensioning high tensile steel wires around concrete pipes. So to make concrete pipes, nowadays they are very common for us, but in 1923 it was first thought from Emperger to wind the pre-tensioning high tensile steel wires around the pipes. In 1924, Hewitt from USA introduced hoop-stressed horizontal reinforcement around walls of concrete tanks through the use of turnbuckles. So turnbuckle is very common for us now to tighten the spokes of a bicycle wheel. Okay, turnbuckle is an instrument to tighten the spokes of a bicycle wheel. So the same is used uh, to the scale of reinforced reinforced bars to induce hook stress in case of concrete tanks. So with that idea of Hewitt in 1924, thousands of liquid storage tanks, concrete pipes were built in the 2 decades to follow. So with this invention. Next, in 1925, Dill from USA used high-strength unbonded steel rods. So this concept of bonding and unbonding of the uh, tensioning rod with the concrete has started in 1925. So the rods were tensioned and anchored after hardening of concrete. So the very basic types of pre-stressed concrete has now come to picture in 1925, what we call pre-tensioning and post-tensioning. So this is what he found was post-tensioning. So early attempt is only pre-tensioning. Okay, now it is post-tensioning concept has come in 1925. So in 1926, what we call the father of pre-stressed concrete, Fressinet. So remember the name Fressinet from France, who is called father of pre-stressed concrete, has used high tensile steel wires with ultimate strength as high as 1725. Now we have started the pre-stressed concrete with 250 megapascal as the tensile stress for pre-stressing. He could go to an extent of you know uh, in fact 5 to 6 times in fact. Okay, so this is almost near to 5 to 10 times of the value that has been used in the earlier stages of pre-stressing. Okay, so ultimate strength as high as what you see 1725, yield stress will be over around 1250. uh, he could use high tensile steel wires. So this is the success story of the pre-stressed concrete, where in 1926 Jean Fressinet has started doing it. 1939, he developed conical wedges for end anchorages for post tensioning and developed double acting jacks. All these equipment are being used nowadays. So he is called as father of prestressed concrete because he is able to use tensile, high tensile steel wires, and he developed the instruments, devices that are to be used in pre-stressed concretes. Okay, right. In 1938, Hoyer has developed long line method for pre-tensioning method, and this has become very popular for making the sleepers of to lay railway line. Sleepers of railway line are now being made with this Hoyer's long line method. And in 1940, Magnell from Belgium developed an anchoring system for post-tensioning using flat wedges, where Fresnel has developed conical wedges, whereas Magnell developed flat wedges. And the early attempts of pre-stressed concrete to use were not much encouraged by the public. Only after the Second World War, uh, then the pre-stressed concrete usage has been picked up as the hundreds of bridges have been built using this concept. Okay, so the history that you can see is spreading around 1820, where the concrete manufacturing started, to around 1920, 1930. So, right. So almost 100 years roughly. Okay. And later on, still some more people like Guyan and Abels, Leonhard, okay, Lynn and Burns. So all these are the famous names in the field of distress concrete. Okay. But later on, the Prestressed Concrete Institute has come up in 1954. Then the prestressed usage of prestressed concrete has picked up, and now you have its application every field of civil engineering. Right. So this is a very brief history how the prestressed concrete is being developed. Okay, we'll go further uh, into discussion in the next session. Thank you all for joining this session.